Hi, and welcome to 8.2 Power. All right, let's get right to it. It says, what is the maximum amount of work that a 4,000 watt motor can do in 5 seconds? Now, the time is 5 seconds. They tell you it's 4,000 watt motor. All right, watt is the unit of power. There you go. Power. Watts. There you go. And the amount of work that you're doing is what they're looking for. Now, watts, right? That's the unit of power. Don't get confused when you're writing a capital W here for watts and a capital W here for work. All right? What are the units for work? Joules. If you do a lot of work, you can buy a lot of joules, and watts are the units of power. Okay, so the equation of the day is P is equal to W over T. And I always ask my students, why are physics students the most powerful students in the whole school? Because they work overtime. They work overtime. That's why they're the most powerful. Okay, anyway, so you got 4,000 watt motor, and how much work can this do in 5 seconds? So you end up just doing 4,000 times 5. So you get 20,000 joules, or 2.0 times 10 to the 4 joules. Or you can say 20 kilojoules. All right, because it's 1, 2, 3. That gives you your kilo, and you're left with 20 left. All right, all three forms both saying all the same thing. Number 2, a 60 kilogram cyclist develops 210 watts of power. If you're on a workout machine, you might see a wattage output. They have it a lot on rowing machines and definitely on the spin machines, the spin cycles. So it says 60 kilogram cyclist develops 210 watts of power while pedaling at a constant velocity of 7 meters per second east. What is the average force being exerted eastward on the bicycle to maintain this constant speed? Well, yes, it's true that power is equal to the amount of work you can do in a certain amount of time. And work is equal to FD. So power is really FD divided by time. And if you look at this, D over T, does that look familiar? It should. Distance divided by time, or displacement divided by time, that gives you velocity. So we actually have 3 equations that we could use for power. Now in this case, they give you the velocity and they're asking for the force, and they give you the power as well. So I'm going to use P is equal to FV. The power is equal to the force times the velocity, and the force is equal to 30 newtons. Luckily, if you have your reference table, you don't have to derive this formula every single time. It is on the back of your reference table. If you look on the back, and if I move my camera down a little bit like this, oh, see, this is why I pause it. All right, you can see we have W equals FD, and it's, we didn't talk about it yet, but it's also equal to the change in the total energy. We'll get to that when we do more kinetic energy and gravitational potential energy. And again, the total energy comes into play. This is the conservation of energy formula. Q is just internal energy. So that's kind of like all at the bottom is the work, power, and energy type stuff. And for this homework, we're looking at these formulas here. We just derived it. Power is equal to work over time. How much work can you do in a specific amount of time? It's a rate at which you could get work done. All right, how fast can you get some work done? And again, work is equal to FD, and work is equal to, so the power is FD over T, and the power is equal to the force times the velocity, because distance divided by time is equal to velocity. Anyway, all the formulas are in the back, nicely derived for you there. So moving on, number 3. Number 3 says a box that weighs 1,000 newtons is lifted a distance of 20 meters straight up by a rope and pulley system. The work is done in 10 seconds. What is the total work done in lifting the box? And what is the power developed by the in watts and in kilowatts? So the box weighs 1,000 newtons. That looks like a backward 7. 1,000 newtons. And you're applying a force of 1,000 newtons. Because, does it say you're going at a constant speed? No, but we can assume so. All right, and you're being lifted a distance of 20 meters straight up in the air. And this occurs over a time span of 10 seconds. All right, so the total work done is equal to the force times the distance. You exert 1,000 newtons over a distance of 20 meters. So the work done is 20,000 joules. And then they want to know what the power is. So this is for A. For B, power is how fast you could get the work done. Work over time. How many joules per second? How many watts? So the power is equal to 20,000 joules divided by 10 seconds. So the power is equal to 2,000 joules per second. I could do 2,000 joules of work every second. Instead of joules per second, you could write 2,000 watts. Now, how many kilowatts is that? You could just do 1, 2, 3 spaces, 2 kilowatts. If you ever forget about that, you just look in your reference table, 2,000 watts times dimensional analysis. We want to get rid of watts, so we put it on the opposite side of the division sign. Watts was in the numerator, so we'll put it in the denominator. A watt divided by a watt cancels out. We want to be left in units of kilowatts. So you look in your reference table at the front page, and it tells you what a kilo is. So let's see. All right. 1 kilo, whatever it is, kilometer, kilogram, in this case it's a kilowatt. One of these bad boys is equal to this many regular meters, regular grams, regular watts. All right, so here we have a 1 kilowatt is equal to this many watts, 1,000 watts. That's our unit conversion. That's our conversion factor. One of these is equal to this many of those. All right, so it depends on what you're talking about. Meters, grams, watts. In this case, we're talking about watts. So you go over here. 1 kilowatt is equal to 1,000 or 10 to the third watts. By the way, if you know the little 1, 2, 3 trick, that's where you're getting that number from, is the 3. So you could do it that way just by looking at your reference table 2. Or you could do 2,000 divided by 1,000 and you get 2 kilowatts. The watts cancel out, you're left with kilowatts. Either way, you get the same answer. All right, so this is in watts and kilowatts. 1 kilowatt is equal to 1,000 watts. That's all you have to know. Number 4. A diesel engine lifts a 2.25 times 10 to the third Newton hammer of a pile driver 20 meters in 5 seconds. What is the power of the engine in kilowatts? All right, so we have the force being exerted is 2.25 times 10 to the third newtons, and the distance being traveled is 20 meters in a time of 5 seconds. They're looking for the power in kilowatts. So power is equal to force times distance over time, work over time. The power is 2.25 times 10 to the third newtons times 20 meters divided by 5 seconds. You get a power of 9,000 watts. And again, you could go through the whole process or just go 1, 2, 3. That's equal to 9 kilowatts. Because 1 kilowatt is equal to 1,000 watts, right? Good. All right, number 5. A rock climber wears a 12 kilogram knapsack while scaling a cliff. After 30 minutes, the climber is 8.2 meters above the starting point. What is the weight of the knapsack? They didn't go very far, by the way, after 30 minutes, but maybe it's taken them a while. So what the weight of the knapsack, how much work is done in joules done on the knapsack? If the climber weighs 600 newtons, how much total work is done? And during the 30 minutes, what is the climber's average power? So you have the climber with so he's got like maybe his little walking sticks with the knapsack. So the climber is exerting a force on the knapsack. The mass of the knapsack is 12 kilograms. I don't know why I'm calling it a knapsack anyway. I always call it a backpack. But whatever, to each their own. The force due to gravity on that backpack is equal to mg. So we want to know what the force due to gravity is so we can know what the applied force going up is. Oops, this is FA. Okay, so they're equal to each other, so we have to figure out what the FG is. Well, FG is equal to mg, so FG is equal to 12 times 9.8, and we want to get full points. So FG is equal to 117.6 newtons. So that means the applied force must also be 117.6 newtons. But this is just for A. Okay. Then for B, it says how much work in joules is done on the knapsack, on the backpack. So the distance that you're going is 8.2 meters up against gravity. This person has to exert a force up against gravity. So the work is equal to the force times the distance. It's 117.6 newtons times 8.2 meters. So the work is equal to 964.32 joules. All right, so that's for B. C is a little tricky. It says if the climber weighs 600 newtons. So now you have the weight of the climber is 600 newtons plus the weight of the backpack, 117.6 newtons. All right, how much total work is done? Well, the work is equal to the total force times the distance. You have the force of the knapsack plus the force of the, we'll call the climber, times the distance. You have to take into account both forces because the person's also pulling their own weight upwards as well as the backpack's weight. If they didn't have a backpack on, they would still have to be doing work, right? So now they're doing the work for themselves. They're exerting 600 newtons of force, plus they're doing work on the backpack as well, 117.6 newtons of force there, times the 8.2 meters, because that's how far we're going. So the total work is 5,884.32 joules. Now, a couple of things to note. I'm not really using significant figures here because I don't like to round until the end. The end game is knowing what the average power is. Also, a different thing to note is, you could have just done FD twice. So this could have been for the knapsack, and then you do the work for the climber. And now we have one work plus this work, and you just add the two together. We already knew what this one was for the knapsack, and you could have just found the work done on the climber itself with the 600 newtons, but then you have to remember to add that to the work done on the knapsack itself. I just did it in one equation here just to show that it could be done that way as well. Okay. D says, during the 30 minutes, what is the climber's average power? So we want to be able to do power is equal to work over time. We did all this work in finding the work, so let's use that version of the formula. So we know the total work divided by the time. 30? No, I don't think so. The time is equal to 30 minutes times, we want to get this into seconds. Again, we could do it the good old dimensional analysis. There's 60 seconds in 1 minute. I put the minutes on the bottom so that they cancel out. 30 times 60 is 1800 seconds. So 1800 seconds, the power is equal to about 3.3 watts. 3.3 watts of power. Okay, number 6. An electric motor develops 65 kilowatts of power as it lifts a loaded elevator 18 meters in 40 seconds. How much force does the motor deliver? So the motor is developing 65 kilowatts of power. You might be able to just look at this and say, okay, 65 kilowatts, that's 1, 2, 3 to the right. So that's 65,000 watts, which you should do. We have to convert this into watts. Another way to do it, I'll just do it on the side here. If you're in kilowatts and you want to use dimensional analysis, you set it up the same way. You have your fraction here, and kilowatts are in the numerator here. We want to get rid of them, so let's put them on the other side in the denominator. That way they cancel out, and we want to get into watts. So again, you look in your reference table, and it tells you 1 kilo is equal to 10 to the third of your base unit. So 1 kilowatt is equal to 1,000 watts. So you get 65 times 10 to the third, or 65,000. And again, the kilowatts cancel, and you're left in watts. Just to show you that you could do it that way in case you're ever lost, this method right here will work every single time as long as you know what the conversion factor is. There's no guesswork involved as to, oh, do I move it to the right or do I move it to the left? You don't have to guess. It's math. That's the good thing about math. All right, so it's lifting it 18 meters and 40 seconds. How much force is being exerted? We could do the work over the time, but we don't have enough information to really find the work. We don't know the velocity, but we're looking for that. We have that, and we have that. So let's use the version of the power formula that has all those variables. At this point of the year, you should, it's almost like when we did kinematic equations where you're just finding a formula that fits everything that you have on your paper. That's kind of why doing the guess method is so helpful. It's a way to keep yourself organized. Now it's just a matter of, now that I know what equation I need to use, it's a matter of plugging in the numbers and then solving. So you get 18F is equal to 65,000 times 3, which is 2.6 times 10 to the 6. And you divide that by 18, you get 1.4 times 10 to the 5th newtons. That's a lot of newtons of force, but remember, we're talking about an elevator. So I would hope that the elevator is capable of exerting a lot of force and is a very powerful motor. That way people are safe. Okay, number 7 says a gardener applies a force of 150 newtons to push a wheelbarrow at constant speed. The wheelbarrow travels 60 meters for 20 seconds. What is the speed of the wheelbarrow? What is the work done? What is the gardener's power? What is the power if the gardener doubles his speed? Interesting. All right, so let's write down, we could make like a free body diagram if we wanted to. All right, we're exerting a force of 150 newtons at constant speed. It travels 60 meters. Okay, and the time is 2.1 times 10 to the 1, or 20 seconds. They're looking for the speed of the wheelbarrow. Okay, so let's see. You don't have to overthink this one. I mean, you might think P is equal to FV. You might think work is equal to FVT. But remember, you're always just writing the given information down so you could figure out which equation you could use. Now, look at the information that we have. Yeah, we have F, but we also have D and T, displacement and time, and we're looking for velocity. That's right. For part A, it's just V is equal to D over T. Don't overthink it. All right, now that you have a lot of equations that we covered on the back of the reference table, you need to be able to think on your feet and know which equations to use when. And again, the guess method is very helpful for this. It helps keep you organized. It helps you see what variables you have, and that will help you determine which equation to use. So you're traveling at 3 meters per second. Okay, that's for A. B says, what is the work done on the wheelbarrow by the gardener? So now that we know the velocity and the time, we could use W equals FVT, or we could just do W is equal to FD, because they give you the force is 150 newtons. They give you the distance is 60 meters. So either one will work fine. And you get 9,000 joules of energy. All right, 9,000 joules of work. Okay, now it says for C, what is the gardener's power in watts? Now that we know the work, we could just do P equals W over T. 9,000 divided by 20. So P is equal to 450. Watt are the units of power? That's right, it's watts. All right, so it says, what is the gardener's power? Good. D says, what is the power if the gardener doubles his speed? Now, you could go through, make this 6. You could do W equals FVT. Then you could do that, or you could even do, you could just plug in, I mean, if you wanted to, F times V, and then plug in numbers, 6. Yeah, we could do it that way. All right. You get 900 watts. But this isn't the way I initially think of it. It says, what is the power if the gardener doubles his speed? And they want to know about the power. So anytime they're relating two variables together, it's kind of helpful to find an equation that relates these two variables together, which we did. We found one that has power, it has speed, velocity. You really only have to look at this equation. If I'm looking at this equation, and this is related to other types of problems that we've done in the past, how are velocity and power related? Is it inverse? Is it direct? Is it an exponential relationship? The answer is that it's a direct relationship. They're both on the same side of they're in the numerator. The velocity isn't being squared. So it's a direct relationship. If I double my velocity, that looks like a square. If I double my velocity, this becomes 2v. I can't just double one side of the equation and leave the other equation untouched. If I double something on this side and it's a direct relationship, I have to double whatever's on the other side of the equation. So now I have 2 times the power. Previously, it was 450 watts, but we want double that power because we doubled the velocity and it's a direct relationship. So all you have to think to yourself is, okay, what's 450 times 2? 900 watts. Now again, you could calculate it with the velocity is doubled. It went from 3 meters per second to 6 meters per second. But it's not really necessary. You could just, unless it asks for you to show your calculations, you could look at the relationship that exists between the two variables. And that's a very good way to do it. All right. Have a good day.